Let
Okay,
me
we are
get my
live.
screen. Okay.
So Rajan, you're going to share your research on baryogenesis. Is that correct?
Yes.
Okay.
Early genesis. I will start with a small introduction to the
Okay.
subject, and okay, let me okay, let me
I'm going to
share the
mute. I'm
screen
going to
first.
mute then.
Okay, and then let me go here.
Yeah, okay. I will mute my microphone so I am not interfering with the presentation of
Oh, no
Rajan.
problem, no problem. Thank you. Okay, see here. Get this. I don't know what's going on. I have to wait a minute to start from the beginning. Okay. I'm sorry. Actually, I should. This is
Rajan, just before you get started there, I'll let you know
yeah. Let
when
me correct that.
I'll let you know when your slideshow is visible. At the moment, we're seeing comments, and so you want it full screen. If you can make it full screen. And,
okay. Okay. Can you see it now?
No, it needs to be.
Oh,
you need to full screen. You're in the comments pane of it or whatever it's called.
Okay. Let me check.
As soon as you get it sorted and you're going to start, I'll mute myself again. Or...
Okay.
Okay, going to present from here.
Yes, Rajan, don't forget to make it full screen the PowerPoint. I mean, press the F5 button so it gets full screen.
Or just
the PowerPoint
also get rid of the stop sharing thing at the bottom. Click the hide button.
Yeah.
And then just start your presentation in the usual way, like start slideshow, and we'll let you know whether it's full screen or not.
1 minute.
Quick edit.
Something went crazy.
Last moment fix. Last moment fix.
Yeah. So because something else was going on. Okay. So let me go there.
That's fine. Can you just hit the hide button on the stop sharing thing?
Okay.
Do you know? Yes, exactly.
Okay. Can you see now?
Yeah, go to your first slide and start the presentation in the usual way.
Okay. Is it showing up now?
No. Oh, no. Just a quick question there, Rajan, as a bit of a troubleshooting thing. Are you sharing your entire screen, or are you just sharing the... you are sharing your entire screen, aren't you?
How about now?
No, you're back to the old...
old problem?
Yeah.
So I will have to go down to the... and then probably increase the thing. Okay. So let me try this way. No, I should have tested this. Sometimes it's kind of a little bit crazy, but okay. How about now? Can you see?
We can see it. Try, you know, if you go down to where the zoom is.
I will increase. Okay.
Wait.
I will increase the...
You see?
No, just press F5 on your keyboard, and this will maximize the PowerPoint presentation. If you press F5 in your keyboard, usually, yeah.
Is it coming?
No.
Same problem. Oh, so the F5 doesn't work. Okay. So let me... I don't know why it is not showing up, but all right.
That's actually fine now. It's okay with that.
Yeah, I had to go back to the... Yeah, I have to see. These days, something's going on. Okay. Every time there is something, always So I go back to my original screen. This you can see, right? I just have to increase the
Yes.
magnification.
Yes, the
What
column
if
on
Okay.
the left.
Rajan, if you go down to the start
Oh, I
slideshow.
can increase the magnification. How about
No,
that?
don't do that.
No, don't do that. Because,
Can I just mention something? If you go to the next to the Zoom thing, there's the little that icon there.
This
Click
one?
on that. Yeah.
How about now?
Well, you see, we can see it, but can you slide the window so that the slide is in the center of your screen or something?
Yeah, that's fine. Yeah.
Still have to do. Yeah.
Is it okay?
Yeah. Go ahead.
Yeah, leave it like that. Yeah.
Okay. So let me just see. The thing is, I cannot see because I have not attached the other one. So okay.
Okay. Yeah. That's much nicer now. Yeah. Oh,
Oh,
you
sorry.
accidentally stopped presenting.
Oh, no
Yeah.
problem. You hit the stop sharing button.
Okay. How about now?
When you share this time, Rajan, make sure you click share entire screen.
Okay. How about now? Can you see? Can you see now?
No, not yet.
Okay. Oh, I don't know what happened. Okay, let me do it again, and then I will do this one.
Make sure you click share entire screen.
Yeah.
Oh, it's not sharing?
Not yet.
Oh, so let me go back. I don't know what. Okay. So it stopped sharing. Huh? Okay. So let me. Okay. Yeah, the computer is kind of slow. I don't know why it's not. So let me go back and start sharing.
Yeah, that's an easy mistake to make. There's the stop sharing button and the hide button are next.
Yeah, they're very close together. Yeah.
I've done that before.
Sorry. Yeah.
Understandable.
Is it coming in now? The
Yes.
sharing coming.
Yes.
Okay. Okay.
Okay.
So now I put the hourglass.
See if it works. I don't know. There's some problem
It's
with
coming
your
up.
some problem with the thing, but
I usually, if Rajan, usually I don't know.
How about now?
That's PowerPoint, yeah, Rajan. That's PowerPoint. Just press the F5. You know, you have the function keys in your keyboard. Just press F5, and PowerPoint will maximize its window. That's all you need to do. Don't use any zoom. Just leave it 100% and press the F5 button. F5.
Yeah, I think we already tried that, Emmanuel.
Yeah, but there is a problem with that.
Yeah, there was a problem.
How about now? Can you see it?
Fine.
No. Yeah, leave it there. Just press hide now. Hide, yeah.
Yeah, that was good. How did you do that?
Yeah.
I hope. Now it's there. You go. Okay. Thank you.
Perfect. All right, I'm gonna mute.
All right. Okay. So today I'm going to present my ongoing research. I think we work together, Emmanuel, Christopher. Thank you very much for being here. All the nice things going on. The Happy New Year with Emmanuel doing his postdoc and I mean a very advanced research towards understanding the quantum entanglement and our superluminal thing. So my presentation partly is that, and then Christopher also has presented advanced ones, the previous ones. So I think our things are coming together, but still we are having pieces of puzzles together, and that's true of physics. So one of the things I am going to start talking about uh, is about. Oh, is this the one I wanted to? Sorry. So I had to pull up another one. I have another slide. Sorry. So I had to pull up the why this came up. Okay. So ensure that, sorry. Okay. I think this is what I want to present because I have like 3 or 4 of them I made. So I think it should be okay. Okay, you can see now, right? Okay. All right. So the early universe, the recent paper I have is, so before I go on, let me pull up this paper. This is the paper I have published in Open Journal of Astronomy, and it is very recent. It's like a few weeks ago, and it contains a lot about what is happening in early universe. So in order to understand why we have to go to early universe, so some things about the physics itself I want to talk about is the perception versus perspective. Perception is observations. So this is a fundamental thing that's coming up with all the top physics. One of them is Bill Gates, recent ones. It prop coming up, and people are having a lot of difficulty understanding why the physics, and there's a problem of quantum mechanics and general relativity, which are the biggest uh, you know aspects of the physics, but they have conflict, as we have mentioned.
Sorry for the interruption. Can you maximize your PowerPoint window as before? Because now it's
it's reduced.
A small frame. Can you maximize the?
Okay, let me check.
Before, yeah. So it.
How about now?
Yeah. That's fine.
Okay.
Yeah. Thank you very much.
Okay. All right. So thank you, Emmanuel, for pointing it out. So the key thing is about physics is observation. So this is the conflict we have: the math and the observations. So what happened was initially the classical physics you have starting with a lot of it is observation, like Galileo observed that, and still we have not solved the problem of gravity. That's what we are compounding. And then later on we started talking about light and things like that, still going on. We don't know whether there's, eventually the understanding was with Einstein and Bohr that the light itself is made of photons. And Newton has suggested about corpuscular theory. So all these are still in the, in the books, it's behind the scenes. These are going on. So we have not resolved that fundamental problem of wave and particle aspect, and it has taken us without much ado. I want to advance it. I don't want to spend too much time on that, except that we observe something like in the night sky, we see points as shining star, as shining points. But then we have the telescope. When you look at that, there's a lot more things to it, right? Uh, and then if for example, at some point we go in a satellite from Earth, outer space, go away from Earth will appear as a point, and we are all living in that inside that point. So it is a lot to do with perception and perspective. So how far away we are from it. Like even when you drive, we do not even go there. Even if when I drive from my point to the other, I see a point way up there. It could be like a hill or something. As we go nearer and nearer, we see more and more features. So I did present something about this physics, observer physics earlier, and Emmanuel, and we all are talking about it. So, but I think it's very important to understand that that's still something that we have to keep in mind, that perception is a function of observation. So, but physics is basically should be based on observation, not on math. Although math is important to bring it out, I think it should be based on observation. I think we are trying to understand it, and with the experiments that Emmanuel and all of us are engaged in, the actual observations are very important. And of course, we have to extend our senses, eye or ear or other senses that we have with which we observe things, with advanced instruments, with probably AI and other things that we think there is a black hole image. Again, people have a lot of misgivings about these things. So we have to somehow address these and try to answer as much as possible. But there are things beyond our vision. I mean, beyond what we can see outright. So, and the perspective then is based on setting and context. So, like I said, if you are far away, a distant object will appear as a point. So it's the same with cosmology, or the other way around in quantum mechanics. We are talking about particles. Again, it's not the particles that we see, in the real life, but the particles we see with a highly advanced microscope, and the highest advanced microscope is the LHC, the Large Hadron Collider. So again, so because of the observations depends on the features point where we are talking about. So the idea is that there may not be anything that is at zero. If you are saying a 0 point, there's something in there. And same with, and 0 point, if we consider as vacuum, there is something in the vacuum. Vacuum is not really empty. So these are the things we can immediately start to rationalize. So the setting context, it depends on the proximity, like I mentioned, whether we are far away, when you go near the observer. So again, relativity talks about observer, aspects completely. Einstein essentially says that it's observer dependent, and Emmanuel, we are discussing about Alice and Bob type of thing. Uh, Again, that's observer effect. And that object, how do we see the object? And is there an interaction? This is where quantum entanglement itself comes into picture. Is there an entanglement between observer and object? That type of thing, and how that. So we have to study that even further. That's a complexation we have. So if example, I said, if you observe a point distance, then while moving towards this, you may see more and more features, and it could be fractal also. There's another dimension to it about fractals. I'm not going to go into that. I basically want to mention these things because they are important for our studies. So analysis is a features, point, or observations. Observer distance is a setting. So there are. I'm not going to even pull up this one, but doing discussion, we can pull up that. One of the interesting things I saw that sum of all the positive numbers. Now, math has some usefulness in the sense that there are some there are things beyond us that we cannot understand, qualitatively, but we have to do quantitatively the math. And also, like, we want to count the number of stars. We cannot really count from a thing. There's more things, right? So we have to use some matrix and some math technique to extrapolate that, what is inside a small unit square, and then we extrapolate what will happen. Now, the question of infinity still comes into picture. So that's a compounding problem. But what interesting thing is that I studied in Absolute Genesis book. Again, I'm going to not talk about that. There was some presentation earlier. They talked about the noise and signal. So the superluminal thing may be appearing as a noise, in the sense that may be where the dark matter is hiding, dark energy, all these things. So could be superluminal condensate, dark energy could be hiding in the noise. So we can never detect that unless there is some kind of mechanism that pulls out the signal. That's the whole idea. So in terms of the math, I recently found that a set, I had to look into that more. It's just mentioning here, a zeta function may be acting, could be acting on the noise to create a error signal, and that creates the universe. So the value of this is like -1/12 or something. So the whole universe. So the error signal what it means that when you sum up that, the error signal is not zero, it's not positive, it's negative, which means it's almost like a negative energy. That's very interesting because that's driving the universe. So that's an interesting thing. I'm not going to go into that, but what it means is that we have to look into early universe. So there is a question about Big Bang. we still are not sure whether there was a real Big Bang or not. But the initial papers that I did with Emmanuel and later on with Christopher said that they could be superluminal things. This is the big thing that we are talking about here. That actually it can be faster than speed of light. And in this paper, again, I'm not going to go into details. In the paper I have, the early universe paper in the Open Journal of Astronomy, I talk about how we can have faster than speed of light without violating the Einstein stipulations. So the standard GR and QFT are incomplete Planck scales, as we know. Magnetic fields are likely fundamental genesis phase. So what we have come up with is, it's not the gravitation that's probably the fundamental thing. It could be the magnetic aspects. So this is one of the things. So the big question is that catch-22 is like gravity. We know is because of the mass. And Einstein said that the mass actually warps the space-time to create the gravity. So that's a catch-22. Which one occurs? What is occurring? Occurring first, which is primordial, which is before that. We believe that based on our thing that it is superluminal with magnetic monopoles in them, and I will show you how we may not observe that in the real universe. So that's one of the theses in my thing that I'm going to present. But this is the other aspect. There is something called Melvin space-time, where it says that the magnetic bending can create a warping. I wouldn't call it space-time at that time. I call it an extent, which eventually becomes space-time, which means without mass. So the magnetic energy density curves space even without mass. So it's a massless bending. It's very, very important because we don't need really a mass to bend the space-time. Then you can apply general relativity and say, okay, once this is bent, then you can create gravity, and that can create the particles, the Higgs boson, and all those things. Rest of the things can follow up. So this may break the catch-22 conundrum. So I have details here about I may not spend too much time. So I use graphics, and thanks to Christopher, I have the Python and some AI programs I use to check things. Again, we have to be very, very cautious about AI. But it does help us with a lot of the difficult task of the literature and survey and also some calculations. But so the embedding, there is an embedding function ZR, and I go into a little more detail in the paper. So I'm just going to mention that here, and the 3D surface curves. So I went through this lot, trial and error method. Finally, I came up with these aspects that I think it demonstrates how it can occur. So as the magnetic density, B, as we know, the magnetic field density, the actual so space curvature, according to Einstein relationship, the curvature of space tends to 1. So because of that, as B increases, curvature increases. Essentially, that's what this equation is saying. The space bulges out. The bulge represents curvature due to higher magnetic energy density, not mass, like I mentioned. So it also shows localized curvature increasing with P. So the curvature keeps increasing, and magnetic field strength. So it depends on the amount of magnetic field, and that's another thing I have calculated, and I go into detail, including appendix and everything, how the magnetic field can reach that level, and there are realistic calculations about that for superluminal condensate. So survey becomes cosmologically experimentally significant. I have a lot of references Mostly it is from literature. My work a little bit there, but lot of I did literature survey of people who have done this about the Lorentz violations, things like that. So essentially, I put together all that in this one, along with some of my earlier research. So appendix shows the how the geodesics Gaussian lensing objects magnetic action demonstrably quantify uh, having thorough visual graphic procs. So essentially, what I mean is here is that the photons can be bent and geodesics can form, and how that happens is what I'm going to do now. The hot PDP, this and the, so that's the next one. The Superluminal magnetic general condensate. I will call it SNGC because I don't want to keep repeating the long name here. So the early universe typically we think that's less than 10 to the power minus 43. This is a Planck level, time. The Planck time uh, contains extremely large energy vacuum fields. So uh, again, in my paper, I do go into some of the aspects in appendix as much as possible, and essentially pulling out from literature how they come up with this understanding. So it's essentially a statement that came out of physics literature study that I had. The superluminal Lorentz violating monopole-driven condensate is proposed. That's the main thing. Again, I have to be humble in saying that. Again, this is a conjecture, or in some ways, an assumption or a hypothesis. How much we can verify, we don't know. But uh, indirectly, we may be able to, like the black hole, we may be able to do that. That's the next phase of the project. And in that one, I suggest some experiments which could pull up that. And recently, another paper, and I have mentioned about laboratory scale measurements, which can replace the LHC measurements to find these kinds of things, including superluminal thing, monopole, things like that. But we have to see how that will go. Again, they need very specific type of instrumentation as well as setups. So the magnetic pole fields, the magnetic produce enormous magnetic field energy densities. That's something I have calculated. This is actually a calculation I have done, derivation calculation. So it does show that, and I go step by step to show how that can happen. So this SMGC is characterized by coherence velocity greater than c. Eventually, you can have superluminal speed. So this is what I have kind of concluded from my calculations, derivations of the calculations. But there's a coupling constant called alpha in that process. So I'm not going to show all the equations here. That will be too time. Mostly, I'm going to discuss the physics aspect with some diagrams. So here it shows, I want to generate more and more graphic plots. I think a picture is worth 1,000 words, so it's better to show that. But only so much we can show. We have to show the math also. But it shows how the superluminal condensate energy density can vary with velocity of the fields. So if the velocity v of c equal to 1, that is just the speed of light. So everything we think is Einstein said you cannot exceed the speed of. Now, Einstein himself has not ruled out. It's the people who interpreted Einstein said, actually emphasized that you cannot exceed the speed of light. Einstein himself was not all that particular about determining the speed of light, but it helps with the special relativity and conservation, things like that. So Lorentz aspects that because it will violate Lorentz conditions. But what we have shown, I think Emmanuel and also we all have shown that, and there are some papers that show that it doesn't really violate Lorentz if we use specific conditions. So there's something called coherence velocity. That's the speed with respect to speed of light. It can go up to much more than one. That's shown here. So what happens to the superluminal energy density? It can keep increasing. So the superluminal condensate energy density, uh, grows quadratically with increasing coherence velocity. So which means that that's what the raw SMGC is the energy density of the superluminal thing. You can write it as, because it has the magnetic force, B square m or mu naught times 1 plus alpha V square m. So this is where our coherence velocity things come to picture. And the alpha is the coupling constant. Uh, so there's a coupling between the condensate and the monopoles, things like that. That comes into picture here, and I have found a way to figure out how we can come up with this thing. So based on these calculations, it's fairly extensive, but I couldn't put everything even in the paper. A lot more uh, I have done before. My notes show a lot more detail, but I have put it as much as possible that can be communicated. That makes sense. Energy density is extremely large due to enormously high magnetic field possible. So again, I show that you can have as much as 10 to the power 18 Tesla. This is a hypothetical monopole high energy scenarios. We know that monopoles can have very high magnetic density, but they come together, they lock in. That's what hot PDP mechanism is. These monopoles come together with some partons or some initial quasi particles coming. They all come together and they form like a circuit, and then they lock in and create that dipole, which I call Horde. So once it locks in, it's like minimum energy requirements that Feynman and other people have said. Once it locks in, then the energy then is released, right, in the form of heat or other things or radiation. So that's how the photons could form, and then you have the dipole. Once the dipole forms, then it doesn't go back because the Gauss theorems, holds good there. So essentially, superluminal thing is a Gauss theorem, Gauss violation of the Gauss theorem that Maxwell depended on. And we know now the violations can occur, like Bell's theorem and everything. So we can talk about violations. So I don't know whether God initial thing is, oh, I'm violating Gauss theorem, so now we have to come together. It's not a joke, but that was quite possible. So initially, it was violating Gauss theorem in some ways, because the monopoles at fast speeds they can go wherever they want, all over the place, right? So it's like a cogmare in which the monopoles are going around, floating around, but at some point they come together. They come together, and when they come close enough, certain critical distance, they lock in and they form the dipole. Once they form the dipole, they release the energy. That's where the radiation, even probably cosmic microwave background occurred from. So my next paper actually talk about that a little more. This is a part one of the paper. Part two, I said that how this can create a lattice type of thing. So locks in the mechanism, forms a lattice. Now, if you go back, how did I get that? Is from a material science background. So I have a material science background where we study very detailed, and because my PhD is material science, corrosion and everything. But we talk about lot about the crystals and how the phase transitions occur from liquid phase to gaseous gaseous phase to liquid, especially liquid to solid. That's where I concentrate for the material science. And there's a fundamental thing about inverse temperature. That's Mullin's-Sekerka interface theorem, where it says that interface initially what happens is that these particles are, and there is a nice diagram also which talks about volume free energy and surface free energy. So initially they going at random, but they come together. When they come together certain distance, atoms, they start forming lattices, and this lattice then forms like an interface between the liquid and solid, and at the interface, they have measured this temperature, or even measured, but there is a nice theory also, complete theory about how the inversion occurs. That temperature goes down near the interface, and little bit further away from the interface, the temperature is higher than the liquid temperature, the average temperature. So you have like almost like it's not a Dirac, but you have very large temperature gradient. And this temperature gradient keeps driving the mechanism to create nucleation first. And once a critical nuclei is formed, after a period, and they have said that there's a critical time, it's a finite time to form the nuclei. And once the nuclei is formed, this because of the temperature inversion, it can keep growing. So this is how we follow single crystal, right? All the electronics now, you need a single crystal, silicon to start with. Now other crystals are there. They all form because you form a seed. You have a seed, because otherwise it will take forever for creating that. So you put a seed, and this crystal then grows the proper planes, crystallographic planes, things like that, whatever you want, 111, 100, whatever crystallographic plane you want, you can create that. So that's my material science background. I think very similar things happened in the early universe. So okay, so essentially what I'm talking about is a hot PDP particle genesis mechanism. So the theoretical context and physical motivation. So one of the big things is the baryon asymmetry, right? All the top physicists agree that the problem of CPT eventually comes to a baryon asymmetry, because we know the proton is the most stable most stable particle, excuse me, in the universe. So you probably formed a early universe. That's where we are trying to figure out. And once it formed, it eventually was a fuel for all the stars or the galaxies, stars and formations. So it provided the hydrogen, provided with the free electrons. They form again. That detail we may have to go through, of course, but the proton is the most stable, and then and then with charge symmetry, things like that, we have the electron that combines to form hydrogen, and also the deuterium, other things, the isotopes. So that up to tritium, and that created the environment to create the fusion reaction, right? And later on, of course, it formed higher atoms according to the periodic table of elements. You have from hydrogen, then you form helium and all other things, all the way to uh, you know uranium and everything, and then we have the reverse process of fission occurring inside the planets. So we can, I mean, a lot of this can be understood, how the stars form and then how the planets form from there. There are still a lot of questions exactly how they form, but I think we have some understanding. I would say only 20%, to be honest. We only know about 20% after we figure out about protons and the stars. We have 20% of understanding how the planets form, and then later on, all the things that's happening within the planets to form life forms. So those things we only know about 20% on a general basis. But I think we have evidence to show that those are correct. So the baryon asymmetry is the big question, and Sakharov was one of the top physicists in the world who came up with the conditions that there's a B violation and a CP violation and departure from equilibrium. So these are the three important conditions. Again, I go to little more detail in the paper, but essentially the hot PDP mechanism, which I described earlier in a paper with Christopher also was involved in that paper with all of us, John Hodge, and many of us were together in that. The hot PDP, and initially I had the Superluminal vacuum, how that 0 points and also micropacols come together. That is one of the first papers I published with the Emmanuel that formed the basis for the rest of them. So everything is built upon that, one by one, built upon that. But everything goes back to that initial paper that I had with Emmanuel, uh, because that contains the essence of how the vacuum and everything comes out. And his previous work also, he allowed me to be a co-author, uh, helped in this process. Uh, so the uses a superluminal Lorentz violating condensates, and I go into details about the map associated with that. I'm not going to present it here, but it catalyzes baryon production via metastable field decays and semi-classical tunneling. So there's a tunneling process, and this has been proved that the tunneling can occur. Tunneling is like degenerate states, uh, you know, uh, on one side, the electrons on one side of the, I call it sometimes of a firewall, but it's like that. And then it can cross over the wall because quantum mechanics allows that. Um, and then you have, energy states which are the same on either side of that wall, uh, or interface, you can call it, and they can tunnel through that wall. So it can go through the wall, the field. So this has been proved uh, with the experiments. And one of the instruments I used, scanning tunneling microscope, uses that phenomena of tunneling. So I know that it is real because that microscope works, and I used for imaging the energies of the surfaces. What happens, electronic structure of the surfaces. That's important for environmental science or the corrosion and things like that. Okay, so the SMGC provides high energy density, enabling false vacuum domains. Again, the question of false vacuum, I think we have to consider in some respects that it could be like a crucible for, and I have presented, and I got a book also recently about futuristic. I presented all of them together, that actually the false vacuum could be playing a role in the high energy aspects to create the uh, the nucleus, which is the formation of hadrons. So it's a high, strong nuclear aspects. So the standard model does, put together all these strong nuclear, weak nuclear, and even electromagnetic to some degree, but it cannot touch upon anything about gravity. So that's why we have quantum gravity, and we are trying to understand that. Okay, so the formal derivation of this baryon, how the baryon can be generated from this SNGC, what I call superluminal thing, and the hot PDP mechanism is given by this equation. I think this equation is derived fundamentally. Again, I'm fairly confident about this equation. I feel good about it. And I think we can utilize, of course, I had to do more research on this, but it gives the how the baryon generation is dependent on the field, as well as what I call the Euclid action things. So the NB here is the number of baryons generated, and phi of xt is the scalar field. It could be an inflaton, Higgs-like, or SNGC order parameter. So maybe all the initially unified field, some kind of a scalar field existed with the SNGC. That's what this field equation is, and this is the d phi by dt squared is the energy, kinetic energy density that is driving the mechanism. So SE is the Euclidean action associated tunneling between vacuum states. So I believe like very similar to Casimir effect, things like that. There's a tunneling of the vacuum states. As we know, the vacuum states are not empty, and it has been proven that particles go in and out of the vacuum state. And H is the reduced Planck constant. We all know that. The equation represents quantum mechanical tunneling probability for a scalar field transitioning from a metastable to a true vacuum configuration, weighted by the energy density. So, the vacuum is dynamic. The overall understanding is that what we can kind of infer is that vacuum is a dynamic creation, not a static thing. So it didn't start with a vacuum per se, but it's a dynamic creation of the kinetics that's going on, the process that's going on, created the vacuum. So that's why the vacuum possibly is not empty. But like I said, the negative energy may be driving it eventually, you know, like a black hole. Way inside the black hole could be a vacuum for all know, dynamically created. But of course, it's going to disintegrate very fast because the vacuum you have negative pressure or even negative pressure to some degree. Then everything going to go and collapse into that, and then it's going to come out like a Hawking radiation type. Okay. So it says this is a semi-classical treatment of vacuum decay. And I feel a little better about semi-classical because quantum mechanics, there are a lot of controversies, but classical physics has a good thing that we can observe most of it. 80% of what the classical physics says we can observe it in real life. But it's the other way around. For quantum mechanics, maybe 20%. Same way, general relativity may be a little bit higher, but classical physics gives the highest level of observations, and you can verify them. Okay, so the next one is we can combine now SNGC, HOD, and PDP mechanisms. So if you think about a domain, typically a simple calculation of a volume of 10 to the minus 36 meter. So I said that you can have a massless bending because the Mel universe, the magnetic bending. I showed the initial picture about that, and that volume eventually it will create like crucible, a small volume where it starts the nucleation process, and that could be like 10 to the minus 36 cubic meter. And then let's say typically velocity could be twice the speed of light, and alpha in this case can be taken to 1 to start with. With more calculations, we may give some other values. I also show how you can approximate alpha equal to 1. And the fields, the energy density fields could be about 10 to the power 30 joules. And the SE, which is the Euclidean action, can be considered altogether order of 1. And we see that, if it is less than that, it's highly sensitive because it's in the exponential region. So when we calculate these values, we get a baryon generation rate of about 10 to the power 26 per second or so. So here SE is the SE actually Euclidean action is the binding energy of the baryonic or color charge excitation, and then you have the Boltzmann constant, the local temperature of the field environment. So then we can calculate this one, and when you put in the numbers, you get about order of 1, but it can be slightly different. But for this purpose, calculation, that should be fine. So these are little bit conservative, they are not over conservative or anything. They are fairly conservative values, which means that we can get that rate with this one. Localized transient baryogenous domains integrate to observe matter content after thermalization inflationary. Now we know that initial epochs contain all kinds of stages, and you have thermalization stage, inflationary dilution, things like that. So, but initially, this baryogenesis process, according to his calculations, are going to dominate all that, and then later on, other epochs start to come in. So I'm going to show you in the next figure how the Euclidean action and barium production will come. So in this case, as SE decreases increasing temperature, barium production goes exponentially. As we know, it's an exponential term. So it is a decrease in the binding energy decreases the barium production, but the other way around, when the value of SE goes down, the production of the baryon, which is essentially protons, right? So they'll go up. So this is how you get baryogenesis or the protons, how they form. and how they become stable. I'm not the next stages after there are like 3 or 4 papers. We'll go into detail how the protons become stable. I think it's already proven, so I didn't go into that, but I think it should come as a natural derivation of these things. How they become stable, and it's still there after billions and billions, so to say, of years. They are, you can put a question mark in all that, because the newer James Webb and newer satellite telescopes up way up in the space shows there are a lot of things that we have to worry about in the astrophysics and also cosmology, the quantum cosmology. Essentially, we are studying quantum cosmology right now. So SMGC domains provide high energy Lorentz violating seed zone. So this is the whole idea. So some kind of a seed is formed. Like I said, analogy to material science, how the solids form from liquids. We have kind of a seed that we use single crystal growth for all our electronic materials. So seed zones, but these seed zones are Lorentz violating ones. But once they form, they can create, much like the Merlin-Zucker formula. We have to come something like that interface, how the interface advances, and then it will support kind of the expanding universe. But again, is the overall universe with the negative energy, like I told you, negative 1 or 12 calculation shows it may be a cyclic universe in the sense that it will expand to some degree and then it will start contracting. It's possible. So it doesn't really say that it cannot happen. So that's the high. So we are going to higher theory to some degree, higher hierarchical aspects. So hot PDP process convert these into condensed matter. So the mechanism, we need to come up with the mechanism. So we know right now Higgs mechanism, but I think we need more than that. We need a next higher level mechanism, and this may be the higher level mechanism, the SMGC hot PDP mechanism. So that talks about how you can create a condensation of matter from initial fields. So initially it could be all fields. Also, they're very noisy. So we can never in real sense, we cannot sense them because their signal to noise ratio is so low, they are not detectable. So that may be the thing, that that's why we are probably not dark energy. We call it dark energy, dark matter, because they are all part of this noise, the superluminal cogmare, which cannot be detected, at least at this point in time. For baryon rate mechanism, the dn by dt equation ensures efficient particle creation. So it says that you can have very high rate of the production of the baryons. So across the early universe volume, observed baryon to photon ratio. So this is again from literature. So baryon to photon ratio 10 to the power minus 10 emerges without extracting. So we don't need extracting new particles to explain them. Like I said, when it locks in, one of the possibility, again, look into later, is that when these monopoles lock in to form the dipoles, they release a lot of energy. They have a lot of energy. And this release energy is the one that eventually comes as a photon or cosmic. So we can connect with that and see how well they work. So there are a lot more things that had to happen later on, but I think this will give a very good, consistent, things across the models to see, and with the equations and the graphs, I think it does demonstrate how these are quite possible. The production of baryons, SMGC, the Euclid action mechanisms. So here the plot shows the Euclid action, like I mentioned, you see, and the temperature, and then you have the you can create the SC. As I said, as the temperature goes up, this Euclid action goes down, Hence, the production rate increases, right? Because it's the negative exponent in the exponential. So as it decreases, the production rate increases. And then you have a critical formation at which the production rate occurs. So we have a critical range at which the baryon production rate happens, and that becomes a stable type of a nuclei. And now, once it forms that proton, it's not going to go back. It's going to stay there, uh, and it has stayed there for billions of years. So, hot PDP mechanism showing Euclid action production rate. Euclid action is the like I mentioned the previous one, uh, the QCD, which is kind of chromodynamics. From there, you can find the binding energy and all those things. The barium production rate is proportional to this rate, increases exponentially as SC drops below 1, representing a transition into a regime where tunneling is unsuppressed, leading to significant efficient baryogenesis with QCD scale cosmological events. This naturally emerges during first order or the crossover phase transitions where metastable domains coexist and decay stochastically. So these a lot of things were going on. I think it's still going on. One can come up with the idea that it never was any change. There was no real Big Bang, but often it's just a condensate. It forms that and goes back into that condensate and comes back. So it may be an eternal process that's going on. Quite possible. Okay. So the magnetic monopole suppression topic, I want to give some few comments about that. Again, I go into detail and I'm going to present all the equations here, but it provides a potential resolution to monopole overabundance predicted by GU. Okay, all the granulified theory said we cannot account for all the energies in the world without resorting to that presence of magnetic monopole. So it has to be there. So this is the final. GUTs come from the other side of the equation, so to say. So we are looking from the others, conjugate side, so to say. So because all the GUTs, everything uses Gauss theorem, Maxwell equation, Lorentz, uh, you know, obeying law, general relativity, and all those things. Speed of light below the, everything below the speed of light, things like that. The special relativity and quantum mechanics. So that's all it uses GUT. But they themselves said that in a way they have violated their own statement about the Gauss theorem. That yes, it has to have violation of the Gauss theorem. Essentially, that's what it means. The monopole will have to be there to account for all the energies. So within coherence epochs, like I said, the monopole fields are confined within the SMGC regions. So again, in the paper, I go into details how they are confined within that. I'll present one, graphic. Again, the graphics are a little more difficult because they are so abstract. But I have pulled out some graphics using because they will, give a little more about the physics than just the equations or statements. So as the universe expands and we become greater, less than speed of light, monopole confinement will cease. So you have exponential suppression of inflationary dilutions. So therefore, we won't expect any relic monopole. So that's one of the reasons we are not able to see astrophysical data, anything about a monopole density, any relic of that, any leftover effects, because as we go there, they all disappear. They become dipoles or the Horde or the dipoles. And dipoles are the key to photons, right? The photons contain the dipoles, and then the electric field is generated from it, uh, and they form this photon, and the waves. You have photon and the phonons forming because of the different uh, movement uh, of the magnetic field and the electric field, which are orthogonal to each other, but which one is rotating, which one is dynamic. If it is dynamic magnetic field or is it a dynamic electric field. So the photons and the phonons, the difference is which one is creating what, which is creating what. So the electric field, we know the moving electric field, a magnetic field can create electric field. And the moving electric field, that's Maxwell equation. And the moving electric field can create magnetic field. So which one occurs first is what determines photon and phonon to some degree. Okay, so possible connection to dark energy and late time cosmology. Again, dark energy has become the say of the present current physics. Without dark energy, you cannot explain a lot of the curves, right? So we have to contend with that. When there's so much study and so much experiment, we cannot ignore them. So we have to take into account and explain those things as well. So the residual vacuum fields from incomplete condensate decay may constitute the present dark energy density. So that's one of the inferences that we can come from it. So the residual aspects, like he said, we don't see the relic per se, but there are residual things that come out of it. And the next paper I talk about lattices, formation of hadron lattices that may contain those things. So that's how everything compressed into that, like a black hole, right? So if a fraction, okay, this calculation is important. I think I will talk about later on. F of primordial condensate. So here the fraction of the superluminal thing, F represents the fraction of that. It's very important. So we get a fraction of that in our real universe or baryon universe, that we get this fraction. So that is about very high, 10 to the power minus 42, and the density is 10 to the power minus 9. So the fraction is 10 to the power minus 51. Again, I show in my paper very clearly how this calculation come out. And this one, we can actually see that is consistent with observed values. So there are some connection to observed values. It's not just a pure conjecture or pure hypothetical calculation, but some of the results does conform to actual observed things. So the validity of this theory is becoming more and more reasonable. It's justified to some degree, because there's a lot more to understand, of course, before we can say this is the theory. So dark energy may thus be a long-range thing, remnant of early universe superluminal content. So that may be how it's appearing as dark energy, which is, according to the current theories, it is the major part. The dark energy, much larger, is the major part of the whole energy system. 70 or more percent of that, and then the dark matter comes into picture. So we have to account for that. Okay. So how the micro black hole, again, like I mentioned, I had the first paper with Emmanuel about a micro black hole vacuum energy. So I'm going back and trying to justify that from this point of view, whether it's justifiable. So it talks about, again, I had to, this is a graphic I could come up with, but as time goes on, we may have, after I do the lattice, we may get a much better plot, but it does, try to explain some other things. So you have the emission rate inversely with mass. So essentially, condensate density and scale emission energy versus micro black hole mass. So we know the micro black hole mass can be very small or can be really very close to the microscopic things. It can be very high. The masses can be very high, very heavy things. So it may constitute the what I call the WIMP type thing, weakly interactive thing, may come out of that. So this is a Planck scale. So we have to always talk about the Planck scale, because that's the lowest level, kind of, where the particles can form. Anything below that will just be a field. So you have to be above the Planck scale. But it could be, I work with Emery about discontinuum physics. It could be much larger than the Planck scale. The actual particle, to form may be much larger than Planck scale level. So the actual critical or stable particles will be much higher than the Planck scale aspects. Okay, so that's ongoing research. So constant threshold having red line is compared with inverse mass emission scaling. Okay, so the red line talks about the threshold above which you have to have this threshold above which only you can have particles. We're having blue dash line, small mass. So the masses are formed like that. So the emission scales then as mass keeps forming as you have higher and higher masses of the micro black hole, then the emission rates comes down. Okay, so radiate intensely, small mass intensity, linking directly hot PDP genesis bursts overall. So it's like a burst that's happening. So burst of thing happen at different levels, and it could be a discontinuum thing or a quantum thing that they are transition. They're not continuous in that sense mainly. So there's a discontinuity, and of course, if you talk about field and particle, there has to be a discontinuity, right? Because we have in between stages, but the in between stages creates the reverse process, and that's the biggest problem, right? The standard model has this problem of particles and antiparticles, and eventually they'll annihilate each other. They won't be in a universe. So how do you get asymmetry? That's a fundamental question. I think this one breaks that conundrum and try to explain how that could happen. Actually, that's the essence of this of this thesis that goes on how it becomes stable and the lattices form and they create again. In that other one, I explained how these hadrons will collide with each other and create a micro gravitational wave, a micro gravitational field, and eventually they will add up, eventually to produce the gravitational field. Like we mentioned earlier, massless spending will the starting point and creates this nuclei, and then as the time goes on, the nuclei starts to form in many different locations. So you have multiple nuclei, and they all coalesce together and they form the bigger one, like a micro black hole. We know black hole theory says that micros, the black holes can create accretion or coalescence and create larger and larger black holes and become supermassive black holes. And that theory is well defined and well understood that indeed they can grow, much like in material science, like I said, nucleation growth mechanism, very similar situation. Because at the interface, you have this driving gradient of temperature and other things, the field, the field inversion happens, and that drives the mechanism of growth. So that's the general thing. The cosmological implication explains primordial magnetism, predicts non-Gaussian early perturbation, provides seeds for large-scale structure, avoids fine-tuning of inflation. So we can understand from fairly simple aspects that the thing. So how does it relate to inflation vacuum dynamics, like we mentioned? Again, I am going to show here from my paper, and it describes a little more there. So if you talk about the radiation aspects, we have the field pressure to energy density aspects, right? So we have W, which is the cosmological equation of state parameter, and it shows the ratio of that. Rapid dilution having expansion occur. That's the cosmological effect, the radiation. The matter where the P is about 0, structure formation epoch. So that's where I'm going to go into the next level of forming the lattices. hadron lattice, so to say. The vacuum energy and cosmological constant. So then it's exponential de Sitter expansions that we think is happening, and the Hubble test, of course, there's a Hubble tension and all. Again, that's complicating situation, but we think at least within the space we have, the universe expanded. But then infinitely, no, probably you have this negative energy driving the mechanism. It's like a feedback mechanism, feedback loop mechanism. The condensate dynamic dark energy, where this constant is between -1 and -1/3, accelerated but non-exponential expansions. So that may be why you have the WIMP aspect, things like that coming in the picture. Okay, the parameter governs how different energy components influence general cosmic expansion through the Friedmann-Lamitere equations. So these are all from literature. A value determining acceleration and the evolution of the scale factor, alpha t. We mentioned the coupling aspect, right? So, so they are all based on fairly justified on the basis of physics literature. So thank you for your attention. Let me show you the summary, basically, essentially Superluminal thing and results, and then some references here. A lot of references. Essentially, it is all there in the paper. So if I go back, yeah, thank you very much. Thanks a lot. So let's go back and we can discuss that. I don't know how much time I took, but
you weren't too bad.
Yeah, maybe little over 1 hour, I think. I probably might have taken.
Yeah.
So yes, thank you, Rajan, for your very insightful presentation.
Whoa.
Oh, thank you. Oh, sorry.
Yes,
I have to
agree. Who better than a physicist which specializes in materials to explain us the baryonic formation in the early universe? So I trust you completely on that.
Thank you.
Yes, because my view of the quantum cosmology is also, by the way, the papers were very excellent quantum cosmology papers, as you said.
Thanks.
And yes, and I'm also in the opinion that the vacuum itself is some kind of, I mean, everything you can say it's a material, even light is a material. So I believe the vacuum is some kind of exotic, unknown phase of matter.
Yeah.
Or energy, whatever.
Yeah.
Which has such properties we in our limited universe, space-time universe, cannot perceive them. So it's a matter actually also of observation. It's true that the closer you go to an object, even if it's a quantum particle, and assuming that it has it's not a dot, it's not just the mathematical point, but it's actually a finite point. As closer you go to the, say you are in a kind of spaceship and some kind of microscopic spaceship, so you can go closer and closer to an electron. As closer you go in, you will see some more futures. Yeah, but we cannot, unfortunately, we cannot probe this fine futures of its energy manifold because the light we're using, it's much larger. The photons, the size of the wavelength of the light is much larger than this presumably futures, small finite futures. The electron we assume it has, and actually every fundamental particle of the standard model. So yes, it's of course it's observation. It's very important. The observer is very important, and actually the perspective, the angle from which you observe the things, which can result totally different conclusions. So perspective and the observer is very important. Yeah. So yes, I agree with you that about the magnetic monopoles in the early universe. I believe also these were the first perturbations in the vacuum energy. I mean the space. First came the space like a soup, and then some structures formed inside, some distortions, which we call normal matter, baryonic, and radiation, and so on. So yes, your description is actually very, I believe, very insightful. That if we say that a magnetic monopole is some kind of vortex, which is a vortex, is a monopole. It has an eye, so it's a vortex inside the space-time. I mean, the space-time soup, the fabric of space. It's not just. I'm totally opposite to the opinion that you have space like a backstage. Everything. No, no, no. Everything is inside the soup. It's distortions of this soup. You know, this liquid. We can say it's a liquid. It's a jello. I don't know what. But it's an exotic type of material. So yes, so you have two vortices, and you can remember there's a very nice video of the physics girl where you have in a pool two vortices, and when they have opposite sense, one spins say clockwise and the other counterclockwise, and they come side by side on the surface of the pool, they form this vortex ring. Yes. So then this is like these two magnetic monopoles coming and making up a dipole. And dipoles is the basis of all baryonic matter we know. It's made from dipoles actually. And yes, and some say that the photons is not a dipole. No, because the dipole, the photon has a spin 1. But you can represent in Euclidean geometry spin 1 like a ring. Yes. So as you in the physics girl video, you see you have this two vortices on the surface, and then underneath you have this vortex string, which connecting the two vortices, and both flowing as one now. Yeah, but this is the half vortex ring is because you have air and water. You have a split there. But if you do a vortex ring with some kind of vapor, a smoke ring in the same medium, air, then you get a ring. But what is this? This is actually two vortices with their apertures joined in, forming a ring. So it's a closed loop dipole vortex. The photon is a closed loop dipole vortex that makes spin 1. And on the opposite side, you have an electron, which is, of course, you have the flux going from the one pole to the other, but the apertures, the two poles are not coming together. You know, it's like a snake biting its tail. That's a photon. So, but the electron is just, you know, this. Also in my papers, this kind of torus spheroid with a hole going inside, but the hole is very small, and it's actually spherical, but you have a diametrical hole joining the north pole with the south pole of the electron charge flux manifold. So yes, I believe that the first things that formed, the first manifolds in this soup, were actually vortices. And vortices are monopole, and these vortices, if they had opposite spin, they came together and formed the dipoles, which is the basis of all baryonic matter and so on. Yes, and as soon as they formed, the first femtoseconds of the Big Bang, yes, then they all joined. So you cannot find any more monopoles, because they have all joined during the first instance of the Big Bang and formed dipoles inside this vacuum energy soup. So, yes, and so I agree 100% with you at this point. And you said also something about coincidence. Yes, the latest DESI calculations, the experiment, the dark, the experiment, the dark, 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 the energy experiment which probes the universe for dark energy. DESI, it's DESI, DESI. I can't remember exactly now the acronym, but it's anyway, it's dark energy surveillance. I don't know. Yes. So they found actually that the state of equation is less than -1, which implies the model of coincidence, which means that yes, the universe expands, accelerate with an accelerated expansion, but giving the cosmological time, this acceleration starts to decay. So it's not that much acceleration. Next year it will be. So this means that maybe the universe will come to a halt, or then again crunch back back to the singularity or so on, whatever. So maybe then you have a cyclic universe. Yes. And what other points I have noticed? You said. Yes, I think I will. You give me time and I remember, so I can pass now.
Sure.
The word to Christopher if he wants to ask you some things.
Thank you, Emmanuel, for wonderful.
For me, it was quite clear.
Yes.
What the conceptually you are talking about, and yes, good, very nice, very insightful theory and analysis, Roger.
Thanks a lot. Yeah. Yes. Thank you for your wonderful comments. I mean, the very apt comments, very the gist of the whole thing.
Yes, but I still have to remember because I didn't sleep well last night, and I'm not 100% today. So I have to remember what else, because I have also some other things now too. But I passed the word to Christopher, and then try to remember something.
Okay.
Okay, thanks, Emmanuel. Excuse me. Yeah. So I mean, I think I get the idea is interesting. You're talking about some sort of field, like energy field, and then matter condenses out of it. So like it's like a fluid, and then it solidifies. So that's a lot like that's a lot. How would you say?
Like phase transitions of matter for liquid to solid, as Rajan said. Yeah.
Right. So what I was trying to say, it's a lot like how in what would you say, general relativity and that they talk about how energy and matter are, equivalent or whatever. And so is that it? Are you really saying that?
Well, yeah, I mean, in a sense, yeah. So, you have to have energy to create matter.
Okay.
And so the energy condenses, so some kind of a condensation mechanism. So this way we call condensate, condensed matter. So you have condensed matter, but it has been proven at the quantum level that these are equivalent, right? At the quantum level, E equal to mc square, but only at the quantum level. So something happens in the macroscopic level, right? It creates heat and everything, and that makes it irreversible. But when you go to a quantum level, it can start reverse itself. The mass can reverse itself to form energy of the scale that we talk about, like a fusion and fission. So like for protons and everything, which is the most stable particle, right? The proton is the most stable. At the level of the proton, it has to be above anything above proton E equal to mc square may not apply. We know that. But E equal to mc square applies anywhere from proton downwards, especially electrons. So which means that energy and matter can interchange, right? So energy can become.
I didn't know that. I mean, like, I mean, it's an odd statement to me. Like, if I have an atom bomb, let's say, and I blow it up, I've converted what? Matter into energy, haven't I?
Yeah.
Now you can say, okay, that only happened on the quantum scale because it was quantum stuff, but then you can say that about literally anything. And then it also implies, oh, well, then the bomb didn't blow up on the large scale, but it obviously did. So I'm not sure about that statement. It sounds contradictory, but maybe I'm misunderstanding.
I think Rajan means fundamentally it's in the quantum level.
Yeah, I know that's what he said. I just don't understand the statement. It doesn't sound. I'm not sure. Like, it does not even matter. I suppose it doesn't answer the question I was asking. Even like, what's so we already have a theory about energy and matter being equivalent. But so I think the key difference, what you're stating, is that it's somehow. Well, actually, I have a different question now, related to you're talking about condensate. So matter is a condensate of energy, but then you're also talking about this superluminal condensate. And if the matter is coming from this superluminal condensate, then that's a condensate from a condensate or something. Is that what you're saying?
Yeah, thank you for your thing. I think many people may have this question. The idea is that in the, if you measure, we see in the macroscopic level energy to matter, right? I mean, we burn fuel, for example, right? So if you burn fuel like a gasoline we use for our cars, we burn that fuel, we get energy, but it's not equal to mc squared there. It's much less than that, right? We cannot convert. Yeah, the energy that we create out of it is a lot less than equal. If you put mc squared the value, it's many orders of less than that. So that's because the c itself is not at the speed of light. Only when the quantum elastic particle has that speed of light, they can move at the speed of light, the particles, right? So they have that level of energy. But when you come to that, our compared to the speed of light, our velocities are many orders, 10 to the power 8 7 or whatever orders of magnitude less. So if you put that value, it becomes kinetic energy equal to mv square, or half mv square is the kinetic energy. So that v is much less than that of speed of light, and hence that energy we derive out of this matter is many orders of magnitude less than that. But when we go up to the level of particles, they are supposed to be moving at the speed of light, quantum relativistic aspects. And that speed, their kinetic energy is so large, right? So that's why the matter and energy are equivalent. Because what is energy? Essentially a field or a wave, right? We talk about waves, that's energy. And the particles, that's a particle wave duality, right? So at those levels, the particles and wave are equivalent. The particles are essentially like waveforms. And that's what the quantum physics is about. Of course, there are a lot of things that, whatever the hypothesis is, depending on that, there are a lot of variations and there are a lot of questions about that. And that's the whole question. The light itself is both a particle and, according to the particle and wave. And the slit experiments, everything proves that in a way. There are a lot of questions about that indeed it can behave as a particle, can behave as a wave. So which means that interchange between the particle and waves are much easier at the quantum level than at our level, the macroscopic level. Because macroscopic level, we ourselves are stable. We don't become energy suddenly, right? So we are stable because the speeds are much lower. So energy that we create is a minuscule. It's a minuscule of the matter. So if we count all the atoms in our body, for example, if you go to the quantum level, each one become energy. The energy we have is enormous, so high, right? It's unbelievable. But we don't get that kind of energy because of that's why I consider the next paper where the lattice. When the lattice forms, it locks in, like the Horde. The monopoles have very large energy, right? But they become the dipoles, their energy levels are much lower. The same way, the next level, the lattices, they form the atoms and they lock in. Lattices, the atoms are locked in. The atoms essentially, let's say, is hydrogen, it's simple thing is hydrogen electron. They form a hydrogen atom, and they form like a lattice. They lock in. So the binding energy is very high. They bind together. You cannot separate them. You need to supply a lot of energy in order to pull them apart. Okay. So the energy that is created out of it is very small. But when you can separate like in vacuum, when the distances are large between them, now they are free to move everywhere, and each one has they can start going at the speed of light. So they are locked in, and the speed is reduced. They are like arrested, or their speeds reduce and reduce because they are locking. The locking mechanism is something that we are looking into, and they lock in, so they stay there, and we call it gravity also, microgravity, things like that. The gravity keeps them in that place, but unless something start releasing them, like in fission process, we have the opposite effect. We bombard with neutrons, and they split up, they make the atoms go apart, and now they are free to move at the speed of light, so they have enormous energy, kinetic energy. So that's how we are releasing so much energy. And we know for nuclear reactor, this is true. Like a chemical reactor versus a nuclear reactor, ratio is orders of magnitude difference, right? And the fission reactor is even more. This we are proving it in the real sense that the energy density is higher and higher as we go, as these are detached, allow them to go free, and then we lock in, then the energy density start becoming lower and lower. So the effective density becomes like a binding energy. They bound together to each other. They won't allow the other ones to move. Their speed reduces, essentially comes to a virtual stop, or very close to zero, right? So um, I don't know whether that explains that. That's one of the ways I can explain how the difference, the energy levels, why it's not equal to hc square in the macroscopic level. Whereas we have proved with nuclear reactors that indeed we can create much higher energy than a regular chemical reactor.
Yeah.
What was the question I asked?
Again? You asked.
I want to add something about, because I think besides with the explanations of Rajan.
Okay, but what was the question? What was the question?
The question is, what is the you say that what is this vacuum condensate and how it differs from material condensate? So
so I'm just wondering.
Yes.
Yeah, because if you have a fluid.
I understand. Yes, I understand. So usually in physics, condensate, like a Bose-Einstein condensate, has a different meaning from condensation. So it's not just something which the density increases. It's some kind. It actually describes a medium where every point in this field, in this medium, is the same. So it's a medium which all parts it's at rest, and it has all the properties in every point in its medium is more or less the same. So it's some kind of homogeneous thing, very homogeneous. So imagine now that you have a bucket full of paint. The paint is at rest, red paint, and this we can say is similar to a condensate. But then when you start to use your make with your finger some kind of manifold, some structure, give it some geometric structure, or take the paint out with a brush and start painting, then you start to make energy manifolds. And this is I say it's some equivalent of the particles of the standard model. And you create baryonic, but as long as it's homogeneous and has not a specific shape, this is a condensate. Because actually, when you read about the Bose-Einstein condensate, it's exactly that. You have some atoms of some gas. Usually, it's gas. It's cooled down to cryogenic temperatures close to absolute zero. And then all the atoms it's like they have joined and created a big macroscopic atom.
Yes.
And then we call that condensate. So in that kind, what Rajan, I assume, also saying is that the condensate, the superluminal, this vacuum condensate has exactly these properties, this fundamental property of a condensate, of a normal condensate. But the energy, imagine now that the energy of these molecules of the condensate are vibrating in a much, these magnetic monopoles, these small vortices are moving are rotating at superluminal speed.
That's confusing though, isn't it? Because I get that. That was a very clear explanation, Manuel.
Yes. Thank you, Manuel. Yeah.
So I understand. So now we have like a condensate, which is very homogeneous, and then that can condense into matter, which is a different thing together.
Locally.
Yes, of course. Yes.
In lumps, you know. Yeah.
That's interesting. But so now, well, so that kind of now I'm kind of a little bit confused on a different level. So if it's homogeneous, and then you're saying so like the paint tin is, let's say it's just sitting there at rest, and that's like a condensate, and then you start stirring it or painting with it, and then so that's a great analogy, and it's very especially when you were talking about the how it pertains to particles as a standard model. That was very interesting. But I'm just wondering, but then at the same time, it seems like what Rajan is, and what you were elucidating about Rajan's theory is that there's these vortices within the condensate. But so is that a little bit of a contradiction, or can you say that if you have like enough vortices, like if they're homogeneous all over the place?
I mean, sometimes I don't know. I mean, I'm just I guess Rajan has to speak. Yeah.
Well,
and then I can add something. Yeah.
Well,
okay.
So yeah, Rajan, do you want to?
Okay.
This is your theory.
That's an excellent description Emmanuel gave about the condensates, Bose-Einstein condensate. See, they satisfy certain type of. I forgot what type of equation it is. Because that's the one that creates that condensate. There is an equation that tells that it has to have the property that Emmanuel mentioned. It has to have a specific property of like a constant field, a homogeneous thing, and it's called a specific condition. I forgot the name of that. We can look up the literature, but it has to satisfy that. So this condensate satisfies that particular equation. Okay. So in terms of the contradiction that you mentioned, is that any random process, I think even Sabine Hausenfeld also has recent one, you can have a totally chaotic order. You can create order from the chaos. And the chaotic thing is the condensate. It has like it's like a homogeneous thing. It's just moving around freely everywhere. And from this you can create order. How? Some local regions, at that point, each like north monopole and the south monopoles away from each other. They are far away from the critical distance. So they are far away from each other. Like I and you are moving, right? I am myself in this room. I can move a lot. But there is another person in this room. My degree of freedom start decreasing. And you have more and more crowding of that. Something happens, And if you think about matter, they start fusing together, right? So that's the idea. So if it is at more than a critical distance from each other, they can move around easily. But as they start to come in the random motion, at some point they start coming together. And when they hit that critical distance, they start locking in. That critical distance is very, very small, extremely small, probably like Planck length or whatever, or even smaller. So that level, they approach either north and south. At some point, they start locking in and they form. Now, if it's just one of them, they will again go back. It's like dilution. They have enough number of them, like a chorus occurring at the same point, everything coming together. Many of them, a lot of them, and then they lock in. Now everything is locked in, and you have sufficient number that creates the local inhomogeneity. So what it is essentially is that from a global homogeneity, you can create a local inhomogeneity due to this random fluctuation. That's the homogeneity is the chaos, right? The local inhomogeneity is the order. that creates order.
Coherence, yes. Coherence is the word. Yes,
Coherence.
I agree. I don't know if Rajan covered you, Christopher. So I mean, even in the paint, you can see that some bubbles are creating on the surface, or even inside the interior of the whole paint bulk, you can have some different localized different intensity, and lumps can form and so on. So you can have from one medium, you can create everything. So I believe everything is created from this vacuum energy. And yes, I mean, space-time itself, they say, is different from baryonic matter. So I mean, space-time, they say, is, I believe everything is space-time. Everything is created from space-time. And when I say space-time, I'm referring to this condensate now as a material.
Yeah, I call it extent. So, that's all.
Yes, and you know, Rajan actually doesn't say anything that contradicts the conventional special relativity and so on, because as I remember, special relativity itself, the theory, allows space-time to go faster than to expand faster than the speed of light. Yeah. And by the way, I don't know if you have ever considered this, the inflation theory of the Big Bang, the first fractions of a second, you have this this condensate, this vacuum, this space-time has expanded superluminal.
Yeah.
I mean, not the light which was created after the particles of light, this energy manifolds and electrons, so on. The space-time now itself, imagine like a vacuum, it's a dark thing. This darkness, this shadow, expanded actually superluminal. This does not contradict special relativity, because special relativity itself allows space-time to move faster than the speed of light. Yeah, it's nothing new, and that's actually now the horizon problem, because how everything is so homogeneous, all the galaxies all around the universe is so homogeneous. If the fastest speed of information of light is c, because first you have the inflation theory, which expanded the how we can say that. So you have some kind of a plate, but this plate first was very small, and then this plate is analogous to the space-time, and then this plate in an instant became large, and now you have dropped some water, and the water tends also to expand, but in a much smaller rate. And the horizon problem asks how this could expand how the universe is so homogeneous. I mean, the stars and all that stuff, not homogeneous, so isotropic. Yeah, how is that possible? So if you can read the horizon problem, if you just Google it in Wikipedia, the horizon problem in cosmology is a big problem. How it does not explain this, and the problem is exactly that. The problem with the horizon problem is that conventional physics says that the all baryonic matter and light is different from the vacuum. It's something different. It's just the vacuum is just a backstage, and then you have this matter inside. It's like you have a room, and then you pour in some dust particles. But the dust particles have nothing to do with a room, with the air, with the empty, with the empty space.
Yeah.
But what Rajan says, and actually my theory as well, is that no, everything is made out from the same energy. It's just manifolds energy, like the painter of the same stuff. And what is the same stuff? Is this vacuum energy, which has many forms. You have 0-point energy, which is Lorentz invariant. It obeys the c-speed limit. But behind that, there's a substrate of energy. The real vacuum is actually superluminal energy. It's out of phase from our space-time, of Einsteinian space-time. We cannot observe it. And we observe it like nothing. As you have also said to you, one of your previous guests, that it's like a fish. The fish does not know that it's inside water.
Yeah, yeah.
For a fish, it's nothing. But
That's
he
it.
doesn't know. Yeah.
I love that meme.
Yeah, nice analogy, Emmanuel. You are really bringing in very nice analogies. That explains the whole thing a lot better.
Yeah.
Thanks.
Yeah, yeah. I mean, I understand all that. If you just said it that way, Rajan, I would have understood it clearer. I think there's a lot of structure in what you're talking about, Rajan, though, and it's like that you bring in a lot of different things all at the same time. It's a little bit overwhelming. It's pretty interesting though. I do have one last question about the.
Okay.
So if energy is I thought it was a very interesting point actually, and I think it kind of links up to what Manuel said about how you were bringing in. What is it? I was just thinking about it there. You know the way you went back to your sort of material science background is what I'm trying to say, and so it sounds like you have this within material science. You know how like we have nucleation around a seed particle in rain, but and then I presume you're saying the same thing can happen in like if you have water and it's close to freezing temperature, it might nucleate around some sort of seed particle or something like that. So that's another analogy, and I think it's a very interesting one. So my question is, what are the seed particles in your model? Or
okay, so you have the initial thing is that bending, because massless bending because of the magnetic field.
Okay,
that's the first process.
Yeah. So just a clarification. If you say space-time curvature bending without the mass, you actually refer to the first seconds of the Big Bang, right?
Yeah.
Not now, not today.
No, early universe.
This happened during the Big Bang. Yes. Yeah. Okay.
Yeah. Yes. But it can happen even now. I mean, it can. I believe
it's more seldom. I mean, you have magnetars and so on. Yeah. But usually not. You need to have a neutron star with a very, very large magnetic field, which actually bends on. It's actually proven that the magnetic field by itself bends space-time.
Yeah.
You don't need matter, because what is matter? It's a concentration of locally centralized energy locally. So even the magnetic field energy, if you have a very strong magnetic field localized in a specific region in Cartesian space, you have mass. It's equivalent of matter again. Yeah. So yes.
Equivalent. Yeah.
But I believe that you're referring the first monopoles, all that the space-time was bent from this extreme magnetic vortices. It's magnetic monopoles.
Yes.
Okay.
So
So go on.
Okay. So that's where where the whole process starts. Now, when it bends that, now what happens is that it helps to bring in the monopoles and form dipoles. The local bending helps them to come together and stay there.
It's like a Mexican hat. The potential.
So they are not going anywhere. After that, they are not going anywhere. They are together. They form this dipole and they lock in. And now they are such a high energy, they can form quasi particles, right? Like positron electrons. That's the idea of hot PDP mechanism. So they start to form like a circuit, like I mentioned, the hot PDP. And
what is that again? It's like one particle converts into another, or
the positron electron. See, positron electron on one side, and you have north pole, south pole, magnetic, right? So you have magnetic field here, your electric field here.
Right. But didn't we have but doesn't an electron have a magnetic moment or something? Does it happen like?
Yeah, it has both electric field and magnetic. The magnetic, we know that it has the both magnetic.
Then what? You have an electron turning into a southern magnetic field or something?
Yeah, I mean the electron, like Emmanuel mentioned, is essentially a dipole. the vortex field. He
No,
mentioned about.
I think it's an interesting idea. I'm just not clear on what does the electron turn into a monopole. No,
I don't know. Reverse. Yeah, that's an excellent point. I'm not sure whether the other. No. I'm not sure.
Yeah,
it may happen eventually. It's possible, but I'm not sure whether electron becomes a monopole. No, the monopole becomes the electron.
Electron. I think electron becomes only a photon.
Photon.
No, okay.
Electron-positron annihilation. You get out two photons with the same energy of the H, which is about 511 kilo electrovolts. So an electron cannot become a monopole.
Unless you supply a lot of energy.
A photon is a monopole. You can say it's a monopole.
Yeah.
Okay. Right. Yeah, I get it from your perspective. The two halves come together to create the electron, so it is a monopole in a sense. So, but so
locked in.
No, it's not a monopole because imagine you have two vortices that come together, and then you have this vortex string diametrically connecting the two polar apertures, north and south.
That must be there. That must be there from the start, though, Emmanuel. Shouldn't it? Even if they're like broken apart and really distant, they're connected, aren't they, by that tube?
Yeah, it's called the Dirac string. Yeah, it was first theorized by Dirac. So they say because it's not possible, according to the mathematics of Dirac in others, a monopole to exist alone. So what Dirac had a very fine trick. I mean, an idea. He said, yes, these monopoles can be imagined like vortices. They can in arbitrary distance apart, but there's always a very thin vortex tube line connecting these two vortices. So this is the Dirac string. It's like, it's the same with the experiment with the water, with the two vortices on the surface. This is actually real. A vortex ring underneath a submerged vortex ring. Water is connecting the two vortices. You just go in Google, in YouTube, and type inside the YouTube engine crazy vortices. That's all. It creates crazy vortices in a pool. Something.
I know them. I've seen them.
Yeah.
I know the concept. I'm just confused. So we got the electron, we got the positron. Then you got a south pole and a north pole. So is this one of these is the monopole of the south pole? One of those is the monopole of the north pole. And are you saying they're all converting into one another somehow?
Yeah, the joint, and then all the flux lines are forming this spheroid, this kind of manifold, spheroid torus.
It's not so what is that? Are we seeing that? But how is the? I mean, if you combine an electron with a positron, you get a photon, don't you?
Yeah, eventually it becomes photon.
This is annihilation. If an electron with a positron, because their charges opposite, if they clash together very hard, then the whole thing unravels. The whole manifold unravels, and two rings come out, which are two photons actually. So the whole string unravels and forms these two rings which fly apart, and each ring has the effective energy of the initial particle. So an electron.
I'm just not sure. I'm not clear how this because you're talking about a circuit though, Rajan. It's an electron to south pole to positron to north
I don't
pole.
know. I'm talking about my theory. I don't know.
I know that, yeah, but he's talking about his one, so I'm just asking general questions. I don't know. I'm just still not clear on that. I thought it was initially very like when you first mentioned it, I was like, yeah. And then the more I think about it, I just
because one of the problem is one of energies, right? Like we mentioned about by electron.
Does the electron turn into a southern? What does that even mean? I'm just not clear.
No. I'm saying that
step one, electron to south pole. What's going on there?
Okay. Okay, they're not aligned. So let me just mention about what Emmanuel talked about. why electron cannot become monopole. One of the reasons is the energy levels. The energy
Rajan, I just want an answer to that straight.
Okay, okay.
To South Pole. What is the connection? I just don't understand the.
No. The electron and positron aligned with each other. Okay, they're aligned like that.
Okay, they're aligned. Where does the South Pole come into it?
They're orthogonal to that. They're orthogonal to this line. Between,
what do you mean that the electron and positron are aligned? In what sense?
Suppose electron is here, the positron here, right?
Yeah.
That's the line I'm talking about. Electron and positron line.
Okay. What does that? What does that tell us?
How they keep apart. See, if they come closer, they annihilate, right? What keeps them annihilating? And that's the biggest problem. How the universe can exist if they keep positron and electron annihilating each other? How can you create universe, right? Nothing will create. It'll keep as soon as they come, they annihilate.
The whole point about what you're talking about is this CP violation that there was like, where is all the antimatter?
Yeah. It's much more matter than antimatter. So this means
I think you need to go.
One explanation I have to read about this is that it was a very tiny percent more matter than antimatter. Yeah. And that's why we observe, and that's this actually initially more tiny percent more matter is actually our baryonic matter in the universe.
That's how my explanation is how you get that matter.
So why
that very small difference?
Yeah, that's the question.
That's why my thing will explain to some degree why that asymmetry occurs.
But you see the way Emmanuel could like express it in like one sentence, some idea, and we all go, yeah, understood that. But then if your idea is going to explain something, it needs to explain it in the exact same kind of way, in one sentence, in a thing that we can all understand. And then we can go, yes, Rajan, you're onto something. But at the moment, I think it's too high level for me. I don't understand material science, and there's too many. As I said, it's just going all over the place into too many areas as well.
Okay.
So I do get the idea of this condensate and the condensation into matter. I think that's solid. I think you can even just grasp that from general relativity in a lot of ways. Possibly further, when Emmanuel's talking about a superluminal condensate, that's something else. That's a new kind of concept outside of general relativity, which is interesting, kind of exciting. So, yeah, and then your seed particle idea is interesting. I don't know enough about whether it's completely accurate, but it is interesting. I will say that. So well done. I hope I didn't grill you too hard there, Rajan, but that's how this.
Yeah, I can understand. See, these are new that it takes time to really, like when we did with the Emmanuel, it took a long time, 5 years, 7 years now.
Like 1 or 2 sentences that are easily unexplainable.
Yeah,
I think I've got it. If you're just talking about, if what I just said there boils down your entire idea, I think that's good. But when you start saying, oh, it can explain matter and antimatter asymmetry, it can explain baryon, baryogenesis, and all these things, yeah, that would kind of. Well, I suppose that is baryon. Is that well? Certainly, it's talking about how it's leptogenesis, isn't it? Because it's talking about how monopoles become electrons, which is Emmanuel's concept. But baryons then are a different thing. They're protons and neutrons. So that is, I'm sure I'll have to go back and rewatch your thing, but I think it's more explained through the medium of some very complicated mathematical equation, which is good. But again, just from the perspective of like saying it in a sentence that we can understand, might need a bit more honing in or something. Just because.
Yeah, I will try this one sentence. Okay. The electric field and magnetic field are orthogonal to each other. You agree with that?
The electron field and magnetic field are orthogonal.
Electric field and the magnetic field.
But that's just basic stuff.
Yeah.
We already know that. Yeah.
So essentially, what is at the ends of this magnetic field? All I'm saying is that what are the ends of the magnetic field at this superluminal level, and what are the ends at the of the electric field? That's it. So the ends of the magnetic field are North Pole and South Pole, and
Right.
the ends of the electric field are positron and electron.
Oh,
That's
interesting. Yeah.
That's
Okay.
it.
I'll definitely think about that more. That's great. Thanks, Rajan.
Sure.
It only took you 5 years to explain that.
I can summarize my superluminal condensate theory with a few words, like cook. So our
Nice.
universe, observable or non-observable, is like a pot of boiling water. So our reality, we are the vapor. And the vapor, the propagation of information is actually C. But the vapor stems out from the water inside the pot, which is boiling.
Mm-hmm.
So by definition, not by analogy more, which matter is more dense, the vapor or the water?
The water.
The speed of sound in which medium is faster? The speed inside water. Therefore, if you want to keep the second law of thermodynamics, our reality or our Einsteinian space-time must stem out from the dark sector. The dark sector is the water, and there the speed of information is much faster than C. So you have our perception, our observer universe, as Rajan said, which we are all made out of light energy, more or less. Everything is condensed light, and it's mandatory that we obey the C speed limit, because this is the speed of it's like the speed of sound in the medium. We are the vapor, but underneath this is a substrate of other reality, another space-time, the dark sector. And as we know from the second law of thermodynamics, the energy flows from the higher state to a lower state. So in the same way, from the water stems out our universe, and the water, the energy there, the speed of information, it's much faster than the speed we observe in our Einsteinian space-time. It's true in our Einsteinian Lorentz invariant space-time, the maximum speed is like the speed of sound in vapor. I don't know. It's C. We are bound by it. This is our prison. This is our prison. But there's another. From where comes this energy? Or otherwise, you say it comes from nothing. Yeah, okay. So the Big Bang comes from nothing. But it's not like that. It's I believe it's another hidden reality. It's a hidden sector, a substrate, from which this our space-time stems out. And when I say space-time, I mean everything we observe and we can measure. All matter, or the light, the galaxies, the vacuum we see. The vacuum we see, it's very important, which we don't see because it's mostly black. But why is it mostly black? Because it's another phase of matter, exotic, totally disconnected from us. I mean, not totally. It still has influence, and I believe gravity is not in the matter, but in the vacuum inside. It's this because everything is vacuum energy. It's made out from vacuum energy. Imagine more like two phases of this vacuum energy. So you have the luminal part, which is this vapor from pouring out from the boiling pot with water, and then you have this water, which is much higher energy. The information travels much faster there. I mean, everything that is going on, and this actually is. I was very impressed with one phrase of Rajan in his presentation. He said, "Superluminal coherence." Exactly. This kind of coherence we need, so we have existence in the universe. You must need a much larger speed of information transfer to keep all this enormous universe we observe, hidden or not hidden, as a coherent system. So the C speed is dramatically a slow speed for the scale of the universe, this large space. So I don't think the C is the ultimate speed limit of propagation of information. I'm definitely, I'm very, I can bet my life on it. I mean, I can bet my belongings. I don't have many belongings. I have just a Punto, a very 30 years old car. So I don't have really nothing serious to lose. But I'm sure that there's according to the second law of thermodynamics, there must be a high reservoir of energy, which powers all the observable universe, all the known universe, not just observed, the known, Yes.
Yeah, very well said.
I'm in total agreement about this point with Roger.
Yeah, of course. Yeah, it's very interesting. It's a lot. It's good. It's a lot to think about. So I don't know. We're at the 2-hour mark. I might drop out. If you guys want to hang back and continue talking, you can.
Yes, I have to just no. I will leave also because I'm a sleepy Joe today.
No problem.
According to
I also
sleepy Joe.
Yeah.
Right. So, guys, I wanted to end with something very interesting I discovered. It's not mine. It's actually the dark superconducting radio frequency experiment in FermiLab, which is made to detect dark photons. I don't know if you are aware about it. I actually
heard of them, yeah. Raja about them as well before, yeah.
So this is very important. It's actually a very interesting experiment. Just give me a few minutes to explain what is all this experiment about.
Go ahead.
So you have two cavities. I don't know, two holes, two cavities, microwave cavities, yes, and you have these cavities at a distance. So they're closed, of course. They're closed. And you have a transmitter cavity and then a receiver cavity. And what is happening now? The one cavity, the receiver cavity, is shielded. It's totally completely, nothing can go in, no radiation, nothing. And you have the transmitter cavity, and this cavity transmits the close proximity together, 60 centimeter center to center. And in one cavity, a very high microwave is created. It's like your microwave oven, yes? But because the first cavity is not shielded, it radiates the microwaves out. So because now the second cavity is shielded, strongly shielded, when they see light in, the theory says that these actually are dark photons oscillation. What is it? It's like a neutrino oscillation. You know the theory about the oscillation that is of the neutrino, which is changing to electron neutrino, then to a mu neutrino, then to a tau neutrino. It oscillates between different manifolds. So the dark photons oscillation, something like that, according to the theory. Not my theory. I mean conventional theory. It's not. There's no consensus, but there are analysis which supports this kind of theory. The dark photon, if it exists, can oscillate between a normal photon and a dark photon. So it's pumping. It's getting dark and then it's getting bright like a normal photon. So what is now happening? When the transmitter cavity, which has a very strong microwave field inside, it's 60 megavolt per meter. So it's a very strong field. And this field somehow disturbs the vacuum energy and creates dark photons. Not just normal photons inside the cavity, but also dark photons, which then fly to irradiate all the surrounding space, and some of these dark photons fly and penetrate the walls of the second the cavity. It's like a wave guide. They penetrate and they go inside unimpeded. It's because dark photons are candidates for dark matter. So they pass through the walls of the second cavity, the receiver cavity, and then inside the cavity, some of them will oscillate and become normal photons, and as soon as they become normal photons, then we can detect them. And now the logic is, but nothing can go inside this cavity. So what are these signals? And the only way is that they are dark photons which penetrated the cavity, and because this dark photon oscillation effect, it became normal photons, and this will prove the existence of dark photons. This will be actually the first proof of dark matter. Because you see, the theory says that these photons are massive. It's not like the spin-1 normal photons, because you have this whenever you have this kind of concept of oscillation, like neutrino oscillation, then this can only happen, theory proves, only if this particle is massive. That's why actually they say no, neutrino is not massless, because you have this known phenomenon, which is established phenomenon, it's actually measured, of neutrino oscillation. Then this means that the neutrinos are not massless, they must be massive. The same applies also for if this dark photons oscillation exists, then these particles are candidates for dark matter. So they have, don't imagine that they have an enormous mass, almost negligible mass, but anyway, they're massive. So yes, and but the problem with which I written to the dark SRF team in FermiLab is that the one after reading the papers, they have 2 papers in archive and also published in I think in physical review letters. It's that they're operating in the far field, which means that the 2 cavities are separated more than 2 lambda distance. So the distance between center to center is more than two wavelengths, because the wavelengths are they're using a 1.3 gigahertz microwave signal. You know the signal inside your microwave is 2.4 gigahertz. So they're using 1.3 gigahertz. And when you measure the diameter, I mean the radius, I don't know, of your microwave is about 12 centimeters, because the wavelength is exactly 2.4 gigahertz, and this converts back to a wavelength of 12 centimeters. Yeah? So they're using 1.3 gigahertz, which is about 3 centimeters in wavelength, and they have the separation at 60 centimeters center to center. But this means that they operate technically in the far field. And according to my experiments and theory, in order to see the dark photons, you have to operate in the near field. So so I propose to these people with my research proposal in ResearchGate to actually to approach more the 2 cavities, about lambda divided by 2, the half wavelength, so the experiment can operate in the near field, not in the far field. That was my proposal. But actually, there is a very good argument against operating this experiment in the dark field, because when you come close, very close, then you are a subject also of another phenomenon, this of quantum tunneling, which according to quantum tunneling, you have these virtual photons which are also penetrating everything. And then you have the problem, these people will have the problem in FermiLab to distinguish between what they're measuring. Are they measuring quantum tunneling, or are they measuring dark photons? So that's why actually I believe they have decided this distance is not arbitrary. They have actually, according to this, tried to keep out the quantum tunneling effects, and so they make sure that what they measure are dark photons and not quantum tunneled normal photons. But now I ask the question, maybe quantum tunneling and dark photons is actually the same effect, the same phenomenon, which is also because then will prove that quantum tunneling is because dark photons. And I said that dark photons are massive. That's why they cannot exceed the speed of light. But this is not entirely true. You see the oscillation. The oscillation makes them massive. We don't know how they behave during flight, because if virtual photons are actually dark photons, theory you have another convention theory, because the conventional theory allows virtual photons in some cases to be non-local, to be superluminal with an upper bound. So I think it's a very important experiment. I'm very excited when I read this experiment, because this is actually a very smart idea to how to detect dark photons. To shield one cavity, make sure that nothing can enter this shielded cavity, and then when you see dark photons, and when you see normal photons, you say how they came in. So it must be some kind from the dark sector. Something came out from the vacuum.
Yeah, that's great, Emmanuel. Thanks for that. I was on the edge of my seat listening to that, gripping, in the sense that you're back and forth between these different ideas. I liked it.
You can read the papers. It's inside my research proposal, inside the research kit. You can find the paper there of this SRF dark. I actually tried to get in contact with 3 of the authors of this paper.
Oh yeah.
They never replied.
Oh, okay.
But I mean, it would be a pity. It would be a pity, because imagine now, in the current state they have detected nothing. They just put stringest upper limits. They say no, we don't have detected any massive dark photon, so we have put an upper limit in its mass. It must be, if there is a dark photon, its mass cannot be larger than that. That's a stringent, but they actually never saw. It's operating now 3 years, this experiment. They never detected even a single dark photon. But they keep all this in the. Let's imagine now that they listen to us, and they close up the distance of the 2 cavities, and then the receiver cavity lights up with normal photons, which suggests that there were dark photons passing unimpeded the walls of the receiver cavity, and then materialized with this effect, this dark photon oscillation became large normal photons, and we detected them inside the receiver cavity. This is if this team succeeds, it's a Nobel Prize, because it's the first confirmation of dark matter.
It's interesting. It's a bit confusing though, because as you say, bring it closer, it could be quantum tunneling, but quantum tunneling could be. So it's like it's kind of unfalsifiable from the perspective of how you framed it.
If you see the apparatus, I don't know entirely all the details. The 2 cavities, you have a cryogenic tube, which is this superconductive experiment. The cavities are operated as superconductors, so they must cool down close to absolute zero. So you have the 2 cavities. Imagine it like UFOs. You have one cavity here and one cavity here. These cavities are, like donut shaped, but they are inside. It's a cavity actually, a donut shaped cavity, and the cryogenic tube is passing through this stuff. So you have one cavity here, and the other cavity behind. So all they have to do is to slide one of the 2 cavities to come closer to minimize this distance. I don't think it's very difficult to do this.
No, I'm not saying it's difficult. I'm just saying that the idea, becomes unfalsifiable because the dark matter photon, as you're saying, could be the tunneling photon.
Yes, that's the problem. I think, but after I read many times the papers, that's actually the problem. Because
but it's also not the problem, isn't it, Emmanuel? It's also the solution, and that's very interesting.
Yes, but I don't. Yes, exactly. It could be that okay. You say, this tunneling effect has a name, a macroscopic name. It's called quantum tunneling, but it's actually measured in our level, in classically. It's called evanescent waves or evanescent field.
Really?
Yeah, and it's a quasi-static field, which has this very funny property that the tunneling is instantaneous. It's a superluminal effect.
Really?
It's very similar to the one I did with a field of a capacitor, which I couldn't measure any time. This evanescent field, actually.
Yeah.
Yes. So it's a superluminal effect, but okay, they will not distinguish if you go closer than 2 wavelengths distance. If you make the two cavities come, then they will definitely see this evanescent field, and they will see light inside the shielded cavity. But then they say, but now what is it? Is it now the normal quantum effect of tunneling we know, or is it dark photons? So there's no way to distinguish between these two.
Yeah.
Actually, the conceptual problem, it's a serious problem. But I ask, as you also very well noted, Christopher,
so
what if it's the same effect?
Yeah.
But then again, you have the problem. Okay, and how you can verify this?
Yes. So you need another level now, another experiment to verify what you're talking about.
I don't know. Yeah. But it's an intriguing aspect, I think. If it's the same effect, because nature plays these tricks to us many times, it's proven. We say it's a different effect, and then we discover that it's actually the same effect.
Yeah,
so
great.
And
it's
the
like
most important
thing. That's great. Okay.
The two comments I want to make about this one.
Go ahead.
Can we do at different? Yeah, can we do at different distances? In the sense, you can do far field, and then near field. So we have many samples, and then you can eliminate the quantum tunneling. From that, you can figure out the contribution to quantum tunneling, and you can deduct that and see whether that responds to the data.
Does it need to be like?
So they can.
Does it need to be
different?
Somehow,
you need a many.
Wait, I'm asking a basic question about the wavelengths. Does it need to be like? It can't be like 1/3 of a wavelength or 1/8.
Yes.
It have to be.
Yeah. You said if the fraction must be indicated, so it's half the wavelength or a quarter of a wavelength.
Thank you. Yeah. That's what I was going to ask.
I think this will also ease the observation, because there you have a trough or a maximum. So maybe it's better to do it in indicator fractals. Not, lambda divided by 3.2, but just lambda divided by 3 or 4. It's best to do it in even fractals. So it's 2
fractions,
or 4,
even fractions, yeah.
Yes. The denominator should be.
Sure, but a fraction can be like, incredibly small and still be even, can't it? So
yes.
So then you could get to your continuous scale that way. I don't know if that's likely.
Yes,
but I'm not an expert on that. So
the problem is they have this 1.3 gigahertz cavities that tuned to. What we mean by tuned to oscillate at 1.3 gigahertz. 1.3 gigahertz is about, I think, 23.5 centimeters. So each cavity must have a length of 23.5 centimeters.
Right.
And they are 60 centimeters apart, center to center. So this leaves a space, enough, in between.
60 or 16?
60. It's more than 2 wavelengths. It's more than 2 wavelengths, the distance, center to center. 60. Yeah, 16.
Yeah.
Not 16, 60. Yeah, sorry.
Gotcha.
But I said that they have to, in order to open the near field, you have to bring them closer together. And the separation center to center must be lambda half, lambda divided by 2, which is 12 centimeter. But now there's a problem now, because if you have 23.5 and 23.5, and you bring them 12 centimeter together, this leaves only a half centimeter cap.
Why do you say that?
Because they have
of course. Yeah.
23.5, 23.5.
Yeah.
And when I bring center to center 12 centimeter, in between the edges, there's only a half centimeter gap.
Right. Yes.
So they're too close down together.
Yeah,
but they're not touching. They're not touching. That's okay.
Yeah.
And you cannot do it otherwise, because if you reduce the size of the cavity, then the frequency, the resonance frequency is not anymore 1.3 gigahertz. It becomes, I don't know, if you shrink it by a factor of 2, then the resonance frequency becomes of the cavity the doubles. It's not 1.3, it's now 2.6 gigahertz.
Right.
And actually, that's what they want to do in the second phase. In the second phase of the experiments they describe, they will reduce the cavities from 1.3 gigahertz, 23 centimeter length, to just shorter.
Yeah.
They increase the frequency. They go to 2.6 gigahertz, which means that now the cavity is a 12 centimeter, about 12 centimeter cavity, not 23 centimeter. But that doesn't solve the problem. The still will operate in the far field, because the distance between center to center will be still 2 wavelengths long.
Right. Okay.
In order to operate in the near field, theory says, not my theory, the distance must be shorter than 1 wavelength.
Right. Yeah. Interesting. Rajan, did you have any more comments you want to make?
Yeah, and so another thing is, when you bring it closer, there could be a problem of heat. It could generate very high thermal heat. I don't know how much heat it can create.
You see, Rajan, the second cavity is shielded. It's complete. So heat is radiation.
Yeah.
Shielded, it will not penetrate. And it's
but the heat.
Cool. Yeah, but it's minus 270 degrees. It's cooled. It's cooled down. So
like
you suppress all the noise. You don't have heating signals. It's cooled almost to 6 millikelvin. It's close to absolute zero.
Okay.
So you don't have this kind of problem.
There's heat sink. There's heat sink.
Interesting.
The heat sink will take care of the.
Read the paper in archive.
Okay.
Yeah.
Okay. Yeah, that makes sense.
Thank you. Yeah. And the other aspect.
That the one I cite inside my proposal is the 2025 paper, but they have another paper in archive, which is 2023. I will send you the 2 papers. I will send you the 23 paper, the 2023, describes the actual experiment. 2025, not so much, because it's already described in the technical details of the experiment. They have also a picture of the whole apparatus. It's more like a quantum computer. You have this column. Similar. Yeah. I will send you, when you finish. I will send you the link to the 2023 paper.
23. Okay.
It's very interesting.
Yeah, that's very interesting. Thank you for bringing it out, Emmanuel. And Christopher, I agree with his statement that about quantum tunneling. Even if they're far apart, still they can do quantum tunneling. I think it's still possible, because they can come near, they can form interface on this side and that side, and they can create degenerate states, and they can still create quantum tunneling.
The width of the barrier, it's instantaneous. The effect of tunneling is instantaneous, and it doesn't depend on the thickness of the barrier.
They have to prove it. They can prove it by different distances. They can eliminate the possibility of quantum tunneling by doing experiments at different gaps. The distance between them.
Yeah, if the separation is too large, then you are sure that you don't have any quantum tunneling.
But actually, you can figure out by this statistical experiment, by doing many samples very, very close.
Yeah. Yes.
You can eliminate you can figure out what is the contribution. You can figure out what is the contribution of quantum tunneling.
Yes, because it must follow some pattern.
Yes.
So that's a good idea, actually. It must follow a formula, an equation.
Yes.
If you don't see, if your results do not comply with this formula, then you actually can say, yes, maybe they are not quantum tunneling, but it's just actually dark photons. Maybe that's the way.
Because the field dependence. Yeah, the field dependence will change. Quantum tunneling depends on, the exponent, the field,
That's
the field.
that's a good idea, Roger. Maybe
Okay, thank you.
maybe you should forward this. I mean,
Yeah,
I don't believe that everything is it's impossible. There must be
yeah,
some kind of trickery you can
Yeah.
do to to discover the truth.
Oh, that's
Yeah.
great. I think you might have solved it, Rajan. Well done.
thank you very much.
Awesome.
Hopefully
This
you
is
want
the
in my
greatest TEGS live streams of all time.
Oh yeah.
I mean,
Hopefully they are watching us.
Rajan, if you have Twitter or Christopher, you can send them a message. Just say at FermiLabs, and then you will send your Twitter, your X message to FermiLab.
Well, that would be great. Yeah, it'd be great to hear back from them. But that sounds very promising, I think.
Actually, I actually have sent them via Twitter, via X, 3 messages. I said at FermiLabs, and I just present my paper there. So maybe some people can read it.
Right, it's FermiLabs. Go, Rajan. Yeah.
Yes,
Let's see it.
Yeah.
Let's see that take place. And come back. Tell us what they said so that we can get an idea.
Yeah, I mean, I keep a track on these guys there, and
Absolutely.
But I'm sure that if they discover dark photons, it will be a headline in news. You will hear it anyway.
Wow, Rajan, you could be in for a Nobel there. And
that's a Nobel. Yeah, whoever discovers the team who discovers
and we are all there. We are all part of the team.
We were present. We witnessed it.
Anyway, now this podcast is a witness. Yeah.
Proof.
Well, we'll have to see. Because but it sounds good. But we'll see how it develops.
It's too early to speculate.
Yes, exactly.
The outcomes.
All right, I'm going to end it there though, because that was good.
Thank you.
Guys,
okay, thank you very much, guys. Fantastic.